What? Hmm?
So this is I got a 1 on. I don't know if he did it, forgot to grade my whole back part.
Oh, maybe he didn't.
That's why I was like, I don't think
I don't know. Talk to her.
okay. Should I email her? Like,
Yeah, scan email to her. Oops.
Sorry, do you know where you know? I can't find it on the syllabus or in the announcements.
It's on your, go to that, Canvas. You should be able to find on Canvas.
On campus.
Yeah. On Canvas, you should have the information of
So
the
that's what I
team.
was looking at. I was looking at, I went to syllabus. No, I was going there and then I don't see anything. I see your email there, but usually how they would have the TA or the grader.
It's go to people. Should be able to,
Oh.
Yeah.
Because it doesn't have her email or anything. Oh, should I just email her and Catherine? Or-
yeah, just email the, on there. Yeah. Okay. Great. Sorry for the trouble. I just wasn't not able to set up the. I was not able to call room meeting in both devices. Somehow won't let me do it. Anyway, so I think we have today's lecture and also maybe one more lecture to one half lecture to talk about feedback, and then we'll move on to something else. So today, we're going to go over the general and practical cases of feedback. So for the last two lectures, we already talked about the generic feedback. We had examples, and then we derived the gain of 4 different types of feedback. Now, the one, of course, we derived in detail for the series parallel, and then we derived all the other 3. And through the process, you already know that you can basically get the a few things that are important. So let's see, slideshow from current. A few things that you probably already know how to get the. So one of the things that you have the open loop gain, and you have the feedback network gain, and then you have the. Why is that happening? And then you have your closed loop gain AF, which is equal to A over 1 plus beta times A. And then you also have your input and output resistance. Each gets changed by why? And you have your RO F equal to RO divided by 1 plus beta times A. So you can see that the input impedance increase and output impedance decrease. And I explained many times why it is good to increase input impedance and why it is good to decrease output impedance. This is for these 3 equations. They are applicable to any feedback, whether it's series, parallel, series, parallel series, or parallel. So it's all applicable regardless of the configuration. As you already know, on the primary, what it means by series, which means it's a voltage, its input is a voltage. If the primary is parallel, which means the input is current, and the feedback is the current, subtracted the current. And if output is parallel, which means the output is a voltage source. If output is series, which means output is a current. So the idea is that you can't put two voltage sources in parallel. If you have two voltage sources, you now want to put them in parallel because the slight voltage difference will cause a circulation current. So voltage is rarely in parallel. Now, of course, we do put batteries in parallel, so it happens, right? But in electronic design, you rarely put voltage source in parallel. You don't put current source in series either. So that's how it works. But the problem is that often you will see the feedback, and you already see examples of feedback like this. The feedback circuit. But this is okay to have a feedback, but the problem is that this is not what we have in the feedback. For example, in the series parallel configuration, we had this feedback as and on this side we have open circuit, on this side we have beta times VO is a feedback. So this is SP feedback. But these two are not equal to each other. So this is the ideal feedback. We have voltage multiplied by beta, get the feedback to the input. But this is a way to get feedback. But this has a resistance. It's not an ideal case. So how do you, in fact, deal with ideal case is we are going to first propose to you this approach. And then we're going to go through example why we did it this way and how to do it. So this is very important to do example, because just in this explanation procedure, it doesn't seem to be very obvious, okay? But anyway, we have to go through the procedure to understand why we're doing that. So to start with the top, that's the generic feedback circuit. It could be ideal, it could be not ideal. So, but in this case, we think it's not ideal, because if it is ideal, you basically can do this. If it's ideal, you would have been doing this as a equivalent circuit. Basically, what happens here? You see, VO, beta times VO, and get the feedback. So the only problem is that we added R11 and R22. If it's not practical, and then we still can use this circuit, but we add R11 on the primary and R22 on the secondary. Then we add two resistance. And this two resistance can be solved by looking at feedback circuit only, the feedback circuit only. So for the R11, for the feedback circuit only, we short the output. And then we look at what is the input. Typically, the feedback is a resistive network. It could be two resistance, it could be three, it could be four. It depends. But if we short the input side of the feedback, we look in from the primary side, we got R11. That's how you get it. So if we want to get R22, we'll open basically this output. Open the output side and look from the input side of the feedback network, because this is the feedback. The input is on the right and output on the left. So open the left and I get this, you see R22. So you get R22. And then for beta, for calculating beta, we would apply a voltage on the input side, think of this as the input to the feedback network, and measure the voltage over here. And take the ratio between VF and VO, that will give you the beta. So once you do 1, 2, 3 steps, so R11, R22, and a beta, then you get that circuit. So that circuit, if you know that circuit, you know that the blue part is the feedback. So if we remove the blue part, what we get is the basic amplifier. Okay, so this is the basic amplifier, and that's the feedback. Now you notice that the only thing that in the feedback is this one. It added this one. If it's ideal, So if it is ideal, and let me write down here, if it's ideal, then R11 equal to 0, R22 equal to infinity. So this circuit will become basically this is your basic amplifier. And if you want to add the feedback, you would simply break this one. If you want to add the feedback, you can break this circuit over here. And you just bring in the feedback over here, which is that's your feedback. So this is very simple. This is your basic amplifier, this is your feedback, and this is your whole basic amplifier, and your feedback is like ideal feedback. The only thing that we now having R11 and R22. And R11 and R22 can be calculated based on using this feedback circuit. All three, R11, R22, and beta can be solved using this circuit. And this method applies not only just to series parallel, but also can be applied to parallel, series parallel, and parallel series, parallel. But of course, the circuit here is these two are going to be slightly different. It's not going to be exact same, but the book gives you really all the details how to do it. Now, this is still kind of abstractive. So my idea is also go through one example, which is also example in the book, to look at how I'm going to identify each of these parameters. So this is a typical feedback of op-amp. We have the op-amps 1,000 times. Every time we have a op-amp input and we have feedback, and we look at ideal op-amp. Sometimes we look at non-ideal op-amps, but this is a non-ideal op-amp. Non-ideal means the gain is not infinity. The gain has limited value. But instead of here, the only thing that we're going to look at it is we're going to use mu instead of A for the op-amp gain. The reason we use mu because mu is the actual op-amp gain. But later on, you'll see we need to find the actual what's so-called gain circuit. What is a gain circuit? It's this circuit. It's this circuit over here. I can possibly make it better to read it, just remove all this stuff. So this is your basic gain circuit. So this is your gain circuit that we will be talking about. So this is your gain circuit. So within this gain circuit, your gain circuit, and you'll find out that your A may not be exactly the same as your mu. That mu is actually op-amp gain. So let's then look at the circuit. So if you look at the circuit, you can see right away, this is output, and this is the input side. So the output is brought back by these two resistors, and this voltage is added to the minus sign of your input. So therefore, this is, so the input side, the input voltage and this feedback voltage is in series. Now, how do you know it's in series? Well, basically, what you can do is, if I add this one, like here, the ground added together, and you can see this is a loop, right? So the voltage is in series. So the primary is, and the output, the feedback is got from here, and the ground is here. So if you look at, again, if it's still not clear for you, you can basically add this ground. So you can see this is your ground, this is your output voltage, which is connected to the feedback, the top of the feedback, and this kind of, so this, if you connect inside, you can look like this, right? So that's what you can do to look at the So the output side is parallel. So this is a typical series parallel feedback. And now we identified parallel feedback. Apparently, this is your feedback network or feedback circuit. So now we need to take this out, and derive those three parameters, R11, R22, and beta. Now this circuit doesn't really change very much, so we can keep it there. We can redraw them. If we want to redraw this circuit, well, first of all, let's do it this way. Let's do draw the A circuit and the beta circuit. So the input voltage is here. And output right over. Let me change this position, make it easy. Okay, change the color. This is our feedback. The beta times VO, and the top here. I'm going to add this resistors. I'm going to also add. So this is our RL, this is R22, this is RO, this is our R11, and this is our RS, this is VS. And this one is mu times VI. VI is from here to here. So it's mu times VI, and then this resistance is called RID, which is the derivative input. And then, so this is your A circuit. And then, of course, this one still has the feedback. If we remove this one, it becomes the truly just A circuit. So this I still has feedback. This actually is a it's not the A circuit. It's actually the overall feedback control circuit includes the feedback. In order to get A circuit, we'll simply remove this one. If we remove this one, like make a short circuit, and that becomes your actual A circuit. But I just leave it like that. And then for the beta circuit, we have it like this. This is our beta circuit. And then we have R1 and R2. So now we need to get, at this point, we can go get R1, R2, and beta. R11, R22, we can, and beta. So this is where I have this A circuit and also the feedback circuit. That's exactly what I draw from the last slide. Now, of course, if you're not so still clear, you can simply add like a line. If that will make you feel better, you can do it that way. The ground will add it all together. So now let's derive R11, R12, and beta. So based on the definition, if we short the, remember how we did it on this circuit here? Is we short here, we look into here, we got R11. So on the circuit that you have this like this, so we'll simply short outside, and then we look at here, we got R11. So this R1, this R2. So when you look at it here, what do you get for R11? You into the circuit, what do you see? You see two resistances, right? R1, R2. How are they connected? Are they in parallel or are they in series? You look from left to right. The two resistance, how are they connected? They're in parallel, right? So this is R1 and R2 are in parallel. Okay, so to get R22, remember we need just open the primary and we look into the secondary. So basically what it means that we have the primary should open. Now you look from the left, look into it. What do you see now? Now, of course, you can say you can have this one here, it doesn't matter. So R22, you have two resistance. Now tell me, are they in series or are they in parallel? They're in series because the other side, basically here and here, they're open. So these two are in series. So this you have R1 plus R2. And then the next one is we get better. You know, to get better, we do this. We go VF, then we apply a voltage source over here. VO. So in this case, so we can write VF as a function of VO. How do we write VF as a function of VO? So VF is from here to here, and VO is here. So if you use VO divided by R2 and R1, you get the current, and then multiply the R1, you get the voltage. So this two is voltage divider. So with voltage divider, you can write VF equal to R1 divided by R1 plus R2 times VO. So this will give you beta equal to VF over VO. That is basically R1 plus R2. Okay, so from here we get beta. Then we already got R11 and R22. So we got all three parameters. It's very simple. And a lot of the feedback is like this. So fortunately, unfortunately, it's very difficult, complicated process. But fortunately, you do have a lot of the circuit just look like this. So it's very simple to get R11, R22, and beta. So now we need to calculate. So for circuit, so we need to get A circuit. So the A circuit basically, again, if we go back here, is the A circuit is simply remove this feedback over here, or simply set this to 0, no feedback. So what is the A circuit? A circuit is no feedback. Well, feedback is 0. So which means 0 feedback, which voltage is 0. Beta is 0, this is 0. So 0 means short circuit, so you can short circuit. So that's your A circuit. So for your A circuit, we already draw the A circuit. Now we need just to redraw the A circuit over here. And we need to find the gain, A, the R in and the RO. So from there, we can continue to do the feedback circuit altogether. So from here, we see that A, how do you calculate A? Well, basically, A is defined as VO over Vs. Now, in this case, if you look, we can do it very easily in 2 steps because we can find out how much V1 over Vi, because this is mu times V1, right? So first step, we find V1 as a function of Vi. So we can find out. So V1 is a function of Vi, the 3 resistance in series. So it's a voltage divider. So we can find V1 as a function of Vi. Because it's a voltage divider, so it goes as Ri over Rs plus Ri plus R22. The first step is to get this V1. And the second step is to get VO. So now you see, this is the voltage. And this RO, this RL, and R22, right? So these two are in parallel. So I can further draw the circuit to be, I just make it a little bit easier for you guys to understand. So this RO, and this is, I can draw them in one circuit to get it RL prime. This is RO, and this is the VO. So you can see that your RL prime is equal to RL in parallel with R1. Let's call it R22 now, so it's make it easy. Because we can plug in R22 later. Oh no, sorry, here it's wrong. This is R11. I'm sorry. That should be R11, not R22. But here is R22. So we put R22 over here. So this RL prime is RL in parallel with R22 over there. And now you can see VO is in reference to this voltage input is a voltage divider, right? It divides between RO and RL prime. So we can say that VO is a function of voltage divider, which V1 times mu. So this is mu times V1. It is divided between RL prime, RO plus RL prime. So now you can plug in V1 to here. So we get mu times V1 is Vi times, there's not enough space. So basically, I just want to plug in this one to get VO equal to mu times V1 becomes Vi, Ri divided by Rs plus Ri plus R11, and then multiply by RL prime, RO plus RL prime. So from here, we can get A equal to, so we send this back, equal to VO over Vi. So it becomes mu times Ri divided by Rs plus Ri plus R11 times RL prime divided by RO plus RL prime. So we got this open loop gain now, which is a circuit gain. Similarly, we can calculate R in and RO. So for input resistance, if you look at the circuit over here, so it's very simple. So Ri is all three resistors together. So we have Ri to be equal to Rs plus RID plus R11. So this is ID. Okay, I have to change that ID. Okay, so this is Ri. How about RO here? You just look at the RO. So RO basically, you short your input voltage source. If you short your voltage input source, mu times V1 becomes 0. So this becomes a short circuit. The mu times V1 becomes short circuit. So it becomes like this. Right? So this is RO, this is RL, and this is your R22. So RO equal to RO in parallel with RL prime, which is equal to RO in parallel with RL prime is RL in parallel with R22. And R22, of course, we know how to calculate. So now we got A, we got R in, we got RO. From there, you can calculate AF, because we know that AF equal to A over 1 plus beta times A, which you plug in all the numbers, you get it. And then we can get RIF equal to Ri times 1 plus beta times A, and you can get R OF equal to RO over 1 plus beta times A. Now we got all these numbers, then we can plug in the numbers to get an actual value. I calculated the value because that R1 and R2 are given. So we can calculate all this A times beta. Let me see what is A value. A is, so we found here A equal to 559.67 and beta equal to 0.0099. Those are the two numbers that we got. So if you assume ideal case, remember, if we assume ideal, which means if we assume ideal, when we assume ideal, what really means A is infinity. So if you assume A is infinity, ideal case, you got your AF ideal equal to 1 over beta, which is equal to roughly 101, I believe. Yeah, equal to 101. So that's the ideal case. But if we plug in all these numbers to here, we got this A equal 559.67 divided by 1 plus 0.0099 times 59.67. We got roughly 99.3. This unit should be volt per volt. Here too is volt per volt. So you can see here, if we assume everything ideal, the case is 101. But if we assume it's not ideal, we got 99.3. So the difference is fairly small, 2%, not very big. And then we can plug in these numbers to get this IF and IOF. So the ROF, because RI was calculated to be 111K, that's what we get from here. So that's what we get from this equation over here. And then also we have RO calculated, which is equal to 11 ohms. No, RO equal to, yeah, forgot to write a number. So we have a value for RO as well, which is in the kilo ohm range. So now we can plug in here to get our IF, which is this here, 1 plus beta times A, and then times RI. We got roughly 6.66 megohm. So which is the 6.6 megohm, significantly larger increase. It's almost like many, like 10 times will be 1 meg. So it's a 60 times increase of the impedance. And RO apparently will be reduced to much smaller number, which is 11 ohms. So that's the numbers we got from this circuit, and you can even further separate the like here. We have RS. So basically, RS is typically the source resistance. It's not part of the circuit. So therefore, sometimes we try to deduct RS from the input resistance, because if you change the source, if you like one voltage source as a certain resistance, you have another voltage source that has another resistance, right? So in this case, the RS will be different. So if you just look at the circuit itself, the resistance will be something like what we call truly input resistance will be IRF minus RS. Because RS is so small in comparison to RRF, you really, the input resistance is very big. It's got 6.66 megohm. Actually, this number was wrong. I mean, corrected. This number this number should be 6.67. And similarly, the output resistance, if you look at the output resistance here, and typically the output resistance does not include RL, because RL is external, is a load resistance. If you change load, the RL will change. But R22 is a part of your circuit. So for the output resistance, you can also remove that RL. But removing RL is not simply minus RL, because if you do that, you'll find yourself in trouble because your output resistance only total only 11. If you minus 10K, how would that work? So it doesn't work. So to remove that output resistance RL from the output resistance, you will have to solve this circuit because the circuit is like this. Right? And here is your RL. These three are in parallel to get your ROF. Right? So really, if you want to get rid of RL, you have to use R out in parallel with RL to get ROF. And RF is given, RL is given. So now you can, from here, you can solve for I out, which is going to be something, let me say, this equation here to be, well, these two are in parallel. You can write out what they are, and then you can, well, basically, if you want to simplify that, you would something like this. So 1 over R out plus 1 over RL equal to 1 over ROF, right? So this is how you write these equations for this one here. So you can take R out is equal to ROF. So basically this ROL R out equal to ROF minus 1 over RL, and then total, you reverse that. So from this equation, we can get this. So this is how you calculate the ideal case. So the process, let me review it so you guys get a better understanding here. The first step is to identify the feedback and the main amplification circuit. And from there, you separate the feedback network. From the feedback network, you calculate R11 by shorting the input side of the feedback network and open the primary. And from here, you get R22. And by applying voltage here, matches output on the output side of the feedback network, you get better. Once you get these three parameters, you can redraw the ideal case by introducing R11 and R22 in the input side and output side. And then you can also draw the basic amplifier circuit by removing the feedback, put the feedback at 0, and you got the basic amplifier. From basic amplifier, you get A circuit, which is called A circuit, or you get the gain, open loop gain of A. And then you start to calculate the closed loop gain, the loop gain, yeah, and then the input resistance, output resistance, and so on. So you can get all these numbers calculated. Yeah, so this is a really example. Yeah, oh, I have another slide actually. That's why I didn't have space. I should have written on this page. But anyway, you guys already know how to do it. Oh, where's the other slide gone? Oh, here. There are another example in the book. Basically, what you really have to do is to identify where the feedback is. So in this circuit, the original circuit over here, as you can see, your input is here and your output is here. So your input, between input and output, you have R2 and R1, connect them together. And this voltage is subtract from this one. And of course, there's also VGS in the middle, right? So, so by looking at the feedback, you separate the feedback circuit, you got this circuit. And from this circuit, you get your R11, R22, and beta, which you know already. This is exactly the same as we did in the last circuit. So by identifying this circuit, the good thing is that for the original circuit, to get the actual gain of the original circuit, you simply would add R11. You see, this is R11. So which is this two in parallel. And also you have R22. Okay, so your R22 is in parallel with RL, which in this case you don't have, you do have RD2, but it's no RL. So once you decouple this, the important thing is R11 and R22. These two are important. Get these two? Okay, now you look at these two circuits. There's no feedback, so you can easily calculate the gain of both stages, this stage and this stage. And the total gain is stage 1 times stage 2, so A1 and A2. Okay? So the idea is that to really break this, because if you don't break this circuit, if you know the video example that I showed you last time, you have to break up the circuit somewhere and to find all the way to the circuit, to get the loop gain, A times beta, they call loop gain. It's very difficult. It's actually very tedious too. By breaking the beta circuit, it makes life really easy, because here you get beta, which is ratio between R2 and over R1 plus R2, and you have R11 input on this input side and R22 on the output side. And from here, you guys probably already know how to solve the circuit, because, for example, if you look at this part, and we can draw the circuit to be, you can use this T model, or you can use pi model, doesn't matter. If you use a pi model, for example, yeah, the second one is probably easier to, let's do the second part with the pi model. So you have input here, and you have this one, and you have this RD2, and here you have GM times VGS2, right? And then at output here, you have really two resistance, which is R2 and R1 in series, and you have your VO. So this is your VGS2. See, from here, you can easily identify, if you want to add RO, you can also add a RO here too. So you can easily get the gain of your second circuit. And for the primary circuit, first circuit, we can also use T model, which becomes, and then you have RD2. Okay, and you can have RO as well connected, and then here you have two resistance. Oh, you have also GM, 1 over GM over here, and you have two resistance R1 and R2 in parallel, and this is your VO1, and then just your V in over here. So now you can find the gain of A1 and then gain of A2, and your total gain will be A1 times A2. And R11, you already know that R11 equal to just R1 in parallel with R2, and R22 is equal to R1 plus R2. And you also have your beta equal to R1 over R1 plus R2, right? So you got all these numbers. Now, you don't even have to redraw the equivalent circuit. You can simply move on to calculate your AF equal to A over 1 plus beta A, blah, 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 blah. And if you calculate RE and RO of the circuit, you calculate RE on this side, you calculate RO on this side. You can also calculate RIF and IOF. So it's very easy to do it once you identify the circuit and break it down to here. So this will be all really for today. And we are going to cover stability next time. The stability, I'm going to cover it very briefly. So basically, what it does that if you have a circuit like this, it means it goes to like a steady state, it's stable. If you have this constant, you know, this is like oscillation. And if you have this one here, it's unstable. So we need to look at in feedback why it's stable, why it's unstable, and so on. So we're gonna get into that next week. So we can go to our quiz early. If you guys get it done early, you can go home early. Hopefully that's the case. You can log into your Canvas. The password is sunshine, SUN, capital S, SHING. So both capital S.